In this video, we'll focus on the hydration of alkynes, or reactions in which we formally add water across an alkyne. And these reactions occur under conditions like those shown here, with only acid and water, or HgSO4, mercuric sulfate, can be included to help facilitate or enable the hydration reaction. And the inclusion of this mercuric sulfate is required for the hydration of terminal alkynes, as we'll see in a moment. For internal alkynes, like the butyne we have here, acid and water alone are capable of enabling a hydration reaction. There are two steps to this reaction that we'll look at. First, the immediate hydration will form this compound in the middle that has an alcohol right next to an alkene. We call this an enol. This intermediate isn't very stable, and it rearranges to the ketone in the step that we call a tautomerization. The first step, the hydration, will look just like the reactions we saw of HX with alkynes. The nucleophilic alkyne will attack the proton, and as that happens, the nucleophile will attack the more electrophilic carbon of the alkyne. In this case, the nucleophile is water instead of X minus. This forms a cationic intermediate, and then deprotonation leads to the neutral enol intermediate. And again, we call this an enol because it's an alkene right next to an alcohol. This enol, though, is not very stable, and so when acid is around, it will undergo an acid-catalyzed tautomerization. And that happens through the following steps. First, the alkene will attack the proton. This is a step or a pattern that we've seen over and over again now. That forms a carbocation, and the carbocation will always form right next to the alcohol. It's stabilized by the adjacent alcohol. The electrons from that alcohol can resonate down to form a new pi bond, placing the positive charge on the oxygen. From here, a deprotonation leads to the final carbonyl compound. And here that carbonyl is a ketone. On the last slide, we looked at the full hydration reaction of the alkyne to the ketone. Here we'll just focus on the tautomerization step. The enol and the ketone are tautomers, and tautomers are constitutional isomers that exist in equilibrium. These are not resonance structures because we've moved atoms. We've moved a hydrogen atom, so they're constitutional isomers. And they're in equilibrium, and that equilibrium favors the ketone. The ketone is more stable than the enol. We should also recognize here that in the hydration step of the reaction, the nucleophile, the water, will attack the more substituted carbon. And that means that the carbonyl, or the ketone, will end up on the more substituted carbon after tautomerization. We noted at the beginning of this lecture that acid and water alone will enable the hydration of internal alkynes. But for terminal alkynes, we need to include HgSO4, mercuric sulfate, to help facilitate the reaction. And the mechanism or pathway of that reaction is a little bit different from what we've seen so far. Here, as always, the reaction begins with attack of the nucleophilic alkyne on the electrophile. But under these conditions, with mercury around, mercury is now the best electrophile. So the alkyne will attack the mercury, and water will act as the nucleophile to attack the more substituted alkyne carbon. This gives us the cationic intermediate that undergoes deprotonation to yield an enol-like intermediate, but one that still has mercury in it. Acid is strong enough to displace that mercury. It will protonate off and be replaced with a new carbon-hydrogen bond to form the enol. Now remember that the enol is unstable and wants to tautomerize. That tautomerization occurs when the alkene attacks a proton to form the carbocation next to the oxygen. oxygen lone pair resonates down to form the new pi bond and a positive charge on the oxygen. Then finally, deprotonation leads to the final ketone product. So remember, in these hydration reactions, when an alkyne is converted to a ketone, there are two key steps. The first is the hydration sequence to form the enol, and the second is tautomerization of the enol to form the ketone. Let's try an example. How would you make the compound shown from an alkyne? This example is asking us to go the other direction, to think about the reaction backwards instead of starting with an alkyne. So here we need to remember that we form ketones from alkynes in a hydration reaction, and that the ketone forms immediately from a tautomerization step. So I might start by drawing the enol that I would need in order to access this ketone after tautomerization. So I might start by counting the carbons in the ketone. Okay, there are 5 carbons. So I'll draw an enol that has 5 carbons and the oxygen on the 4th carbon. And now after tautomerization, this structure will lead to the desired ketone. Now I need to go backward one more step and think about the alkyne that could give rise to this enol. So I'll draw an alkyne that has 5 carbons, where the 4th carbon is the more substituted carbon of the alkyne. In this way, I can be sure that the oxygen, the nucleophile, will attack the 4th carbon. If the 4th carbon isn't the most substituted or the most electrophilic, then I won't end up with the right product. So here that means I need a terminal alkyne. Now when this terminal alkyne is treated with acid and water, the desired enol in blue will form. So overall, I can make this ketone by treating 1 pentyne with water and acid in the presence of HgSO4. Remember that because it's a terminal alkyne, I need the mercury to help facilitate the reaction. Now we'll end this lecture series by answering the question we saw at the beginning, to predict the products of each of the following reactions. We'll tackle these reactions one at a time. First, the addition of HCl. The alkyne will attack the proton, and at the same time, the chloride will attack the more electrophilic carbon of the alkyne. This will add the hydrogen and chlorine across the alkyne in a trans fashion, with the chlorine added to the more substituted carbon. In the second example, addition of a halogen, the alkyne will attack the bromine to form the 3-membered ring intermediate. From there, the bromide anion will attack the more substituted carbon to open the ring, and overall, the 2 bromines will add across the alkyne in a trans fashion. Finally, in the hydration reaction, the alkyne will attack the proton and the water will attack the more electrophilic carbon of the alkyne. This will yield the enol intermediate after deprotonation, which I'm not drawing out in full here, but it does still occur. Then the enol undergoes tautomerization to yield the corresponding ketone product.